Alright, so continuing with our videos on derivative rules for Math 1560, Calc 1 at U of L, we're going to move on now to the product rule. Now, one of the easy mistakes to make with the product rule when you see this for the first time is to assume that the rule for the product of derivatives is going to work like the rule for a product of limits. After all, the rules are the same for sums and for constants, whether you're dealing with limits or derivatives, right? So for both limits and derivatives, the sum rule is, the limit of a sum is sum of the limits, the limit of a derivative of a sum is the sum of the derivatives, and then both for limits and derivatives, both of them have rules saying that you can pull constants out. Then you get to products, and you might reasonably think that the derivative of a product should be the product of the derivatives, but this, in fact, is not true, and really none of calculus would work if that were to hold. So we can see that the rule is actually quite a bit more complicated, right? So the derivative of a product, f times g, you take the derivative one function at a time. So you do the derivative of the first one, and then you multiply by the second. So notice that we only have a derivative on one of the two terms, right? And then the second term, we take the derivative of the second function, right? And if we had three or more things multiplied together, again, you would follow the same pattern of if there's going to be, if we have three functions multiplied together, we're going to get three terms in the derivative, and each one of those terms is going to contain the derivative of just one of these functions. So the way this works is, just to give you an example, let's say we want to do the derivative of, now we don't have very many examples at our disposal yet, but let's do a silly example so we can see that this makes sense. Let's say I'm doing x cubed times x to the fourth. All right. So the product rule says I should do the derivative of x cubed, and then I multiply by x to the fourth, and then I should do x cubed and multiply by the derivative of x to the fourth. So I get 3x squared times x to the fourth, and then I get x cubed times 4x cubed, applying my power rule to each of those terms. And notice if we kind of combine things up, I get 3 times x to the sixth here, and then I get 4 times x to the sixth there, right? Multiplying powers, we add the exponents. 2 plus 4 gives me 6. 3 plus 3 gives me 6. And then 3 times x to the sixth plus 4 more leaves me with 7 times x to the sixth. And of course, that makes sense because x cubed times x to the fourth is x to the seventh. And we know how to take the derivative of x to the seventh using the power rule. Okay, so this makes sense. How do we see that this is true? Okay. Well, let me see. Okay, I do have a proof coming for you guys. So let me just warn you, okay, that the derivative of a product is not the product of the derivative. So let's think of a simple example. We already know that the derivative of x squared is 2 times x, right? So what if we were doing, what if we wrote x squared as x times x? So, well then, I should, the product rule says I should do the derivative of x times x plus x times the derivative of x, and that gives me 1 times x plus x times 1, and I get 2x as I expect. But what if I wasn't paying attention and I just did the derivative of x times the derivative of x, right? Well, then I would just get 1 times 1. I would get 1, right? So that obviously can't work, right? If this were true, then the derivative of x squared would not be 2x, it would just be 1. And in fact, we could kind of extend from here and we would say, well, in fact, the derivative of any power of x seems to just be 1. Well, that can't be right. We know that the derivative of a power is not always 1. There's a power rule, it's more complicated, and so we need to treat products very carefully. You can't simply take the derivative of each term in the product and multiply them together, right? We have this much more complicated rule, okay? Let's do a few more examples. If we do the let's say f of x is equal to, let's say, x squared times the square root of x. So remember that the derivative of the square root of x, we've seen this now a few times. It's 1/2 x to the minus 1/2 using the power rule. We can write that as 1 over 2 times the square root of x. So the derivative is going to be, so we do the derivative of x squared times root x, and then we do x squared times the derivative of root x. So we get 2x times root x, and then we get x squared times 1 over 2 root x. Okay. Of course, we could simplify this if we wanted to, but we can leave it like that. It's fine. You don't have to simplify this answer. What's another one we've seen? Another derivative that we saw is that the derivative of sine x is cos x. So if we had, say, let's say g of x was equal to x squared plus 1 times sine x, well, what's g prime of x going to look like? It's going to look like we have to do the derivative of x squared plus 1, and then we do x squared plus 1 times the derivative of sine x. So that first derivative is just 2x. So we get 2x sine x. Remember that 1 is a constant, its derivative is 0, so we just have the 2x. And then we get x squared plus 1 times cos x. Okay, now let's come to that proof, which I thought I had put earlier in the slides. Sorry about that. You can tune out now if you don't care about the proof, but if you're curious how this works, it goes something like this. So let's say that we can write our function as a product, so h looks like f of x times g of x. So we know what h prime should look like. It looks like the limit h going to 0. Maybe I shouldn't call this h. Let's call this thing k. It's not gonna be around very long, just because I don't want to have two h's. So it's going to be k of x plus h minus k of x all over h, right? But we know that k is given by f times g, so this is going to be the limit. H goes to 0. F of x plus h, g of x plus h minus f of x times g of x all over h. And now we use a kind of clever trick, dirty trick, however you want to think about it. It's not something that you might necessarily think to do, but this is something that has been figured out a very long time ago by very clever people, and we just kind of have gone with it ever since. What I'm going to do is I'm going to first subtract and then add. So I'm going to do f of x times g of x plus h plus f of x times g of x plus h minus, I still have that f of x, g of x in there. And maybe now you can see where this is going. We're going to do some clever regrouping. So what we're going to do is we're going to move things around like follows. Okay. So notice that these two terms here, they both have this g of x plus h in it. So if I factor out that g of x plus h, I'm left with f of x plus h minus f of x. I can divide by h. That's exactly the derivative of f. And I'm going to apply limit properties as I go. I get that. Now I notice that my other two terms, there's a common factor of f of x in there. Okay, and remember my limit is with respect to h, so as far as the limit is concerned, f of x is a constant, so I can just bring it out of the limit. And I get the limit h going to 0 g of x plus h minus g of x all over h. All right, do you guys see it now? Do we have it? Well, we know that that first term there is just going to be f prime of x. What about this one? Why do I know that this is g of x? It is, but I've got a limit there. H is going to 0, g of x plus h. Why do I know I can just put h equal to 0? Well, the fact that I can put h equal to 0 there relies on the fact that g is continuous. Why do I know that g is continuous? Because I'm assuming that the derivative exists, and in an earlier video we showed that every differentiable function is automatically continuous. So continuity lets me put that g of x in there. Okay. That guy is already f of x, and what's that last limit? That last limit is just g prime of x, and we're done.